nearly 1,000. So you use that to compare two music items in a large database. That's very inefficient. And the same difficulty remains here. You can't come up with enough keywords to describe the music content. Yeah. So after we have gone through the three categories, we may ask ourselves whether it's possible to model. We have so many aspects. Is that possible to model each of them? And is that possible to come up with an adaptive measure so that the users can easily customize their preferred music aspects to retrieve music? And if you break the big question, we will ask the following questions. Can we model each music facet separately? If so, will we have a simpler music feature type for each facet? Will it have a smaller dimension or something like that? Or can we use the most efficient indexing algorithm for each of such features? If so, will that enable personalization of music similarity measures? Personalization here, we mean we can adaptively use the most user-preferred music facets to measure the similarity. So the following talk is by and large guided by those questions. We will see how those questions can be addressed in our framework. And then we'll talk about some details about the framework. This is the overall flow chart of the framework. Here is the user side, and here is the, we can say, server side, the database. In between the database and the user, we have the user input, either the music query or personalization profile, and then followed by the query analysis, indexing, and then query results feedback. Actually, in this framework, the main contribution is that we propose we constructed some feature vectors to describe each music facet separately. Here is the different feature types. We'll talk about the details later. And then, based on those feature types, we define a music similarity measure to rank different music results. And this is the module to construct the music features, either from the query or from the audio items in the database. And then that's the indexing structure, content ranking, which implements the similarity rank. The personalization, we'll see all those modules later. Okay. The first part, let's take a look at the different feature vectors for different facets. In this work, we mainly focus on two modalities, text and audio. In text modality, we just take a document vector from text retrieval field for granted and use it to model the metadata. In this way, we can model the metadata as a whole in one document vector, or we can separate the metadata into different fields. For example, in comments, title, description, we can model them separately, but we can model them as a whole. The contribution here is that we define a new feature vector to describe the content-related aspects. In content-related aspects, we have generally two kinds of aspects to model. For music, one aspect is that you can define a class terminology, or you can define a class hierarchy to describe that aspect. For example, genre. So normally the most popular genre styles, we have around 8. For example, rock, pop music, classical music, etc. For that kind of music aspects, we can define a meaningful class hierarchy to do that. And also mood has such property. But for some music aspects, we cannot define a class terminology. For example, tempo. Here we say tempo is a music value describes the speed of the music beats, how many beats per second. So it's really just a value. We cannot define classes based on that. Also melody. Melody is the in a very, how to say that, in a very naive term, is the sequence of the node sequence. So in that case, we don't have any explicit classes. What we can do is to recognize the node sequence from the audio content and use that as a feature vector to represent that music aspect. So this is a pictorial illustration of the different music aspects. So if you think each aspect is a dimension of a music description space, here in this axis we have a genre dimension, which corresponds to the genre aspect or the genre facet. Each block here corresponds to a genre class. So the signature is of a series of probability values represents the probability of a certain music belongs to this genre class. So in this way, we can characterize different music items into different genre feature vectors. That's for mood, and here is for document vector. I don't know whether you are all familiar with document vector. Probably for you, yes, right? And document vector is, I won't go into the details, so if you are not familiar with, you can easily look it up. The basic idea is it represents whether a word appears in a text field. If that word appears, that's 1. If not, that's 0. So we use that as a feature vector. What's the good thing about this kind of representation? For this kind of feature to represent the content aspect, it's good because it represents the fuzzy nature of human perception. Human perception to music meaning is fuzzy. Whenever I ask you, if I ask different people to, assign a genre style to a certain music, not all of them will give a single genre style. They may give different style labels. If I ask you today or tomorrow, what's the genre style of this music, you may give me different answers. So in this case, we just focus on the probability distribution of different genre styles. So it's kind of more, it's a closer representation of the human perception of music meanings. And also it's well structured because if they only focus on the genre class, the dimensionality will be relatively small. And later on we can use a separate indexing structure to index only the genre aspect. And also it's human understandable. If I tell you each of these blocks belongs to which genre style, later on you can easily see the actual music meaning of this music. And also it allows direct human-computer interaction. And third is flexible. In different applications, you may come up with different number of classes to describe the music. Okay, based on those features, if we have one feature vector to describe each music facet or aspect, for each music item, we can abstract them as a feature vector set. Each feature vector is describing each music aspect. And if we just use a very simple metric to define the distance of any single music aspect, and later on, based on this distance measure of single aspect, we can allow users to choose their preferred. This is a personalization profile. PI is the index of the aspect user may choose, and this is the weight of that aspect. So based on the single distance measure of a particular music aspect, and based on this personalization profile, then we can come up with a personalized music similarity measure, which is just a summation of all the, basically, essentially the summation of all the individual music similarity measures that the user has chosen. So this is, the concept is clear to everyone. You don't need to pay attention to the details of this formula. You just know we measure the distance along each aspect and